So we are just past 10:30, so we'll go ahead and get started. Let me find my... Okay. As many of you are familiar, first of all, welcome everyone and Happy New Year. As many of you are familiar, one of the things that we do here in the Science Education Department is large-scale nationwide research on various topics pertaining to education. This talk discusses some of the results of one of those large-scale NSF-funded studies. For a society more and more dependent on high technology and therefore its subsequent well-being, it is crucial to have both a large and diverse cadre of competent computer science professionals and a computer-literate citizenry. Toward these goals, sweeping initiatives have been underway to boost the young generation's exposure to computing, as many of you have noticed in the past several years. This seminar presents findings of a large nationwide survey of over 6,000 beginning college students at 59 institutions about the influences of a wide range of in-school and out-of-school experiences with computer science on students' computer science interests, as well as their computer science identity. We're pleased to welcome Drs. Gerhard Sonnert, Susan Senberry, and Raju Wu, all members and researchers in the Science Education Department here at the Center for Astrophysics. Dr. Sonnert is a sociologist of science and of gender. As a senior research scientist in the SED here at the Center for Astrophysics, he's worked on a number of large-scale national surveys investigating factors influencing students' STEM identity and their career interest in STEM professions, as well as success in intro college STEM courses. He's also a lecturer in the astronomy department here at Harvard, teaching a course on astrosociology. Dr. Senberry is also an educational researcher and project manager here in the SED. She has a doctorate in education and a bachelor's of science in marine biology from Boston University, and also a master's in education, elementary education from Lesley University. With more than 30 years of experience in the development and implementation of formal and informal research, as well as evaluation projects, she's also been a K-8 science educator and science coordinator. And finally, Dr. Wu is a PhD graduate in quantitative and psychometric methods in educational psychology from the University of Kentucky. She is currently a postdoc researcher here in the Science Ed Department. Her research interests include large-scale assessment, computer science, and STEM education, multi-level analysis, and item response theory, or IRT. Going forward, please feel free to post questions in the chat. We will address questions at the end of the talk. We also ask that if possible, people please leave their cameras on during the presentation. Without further ado, please welcome our presenters, and I will turn it over to Gerhard to get us started.
Hi, good morning, everyone. Thank you for coming to our talk. I'm the principal investigator of this project, and I will start the talk. Then Sue Sunbury will take over, and last but not least, our postdoc, Raju Wu, will present the results. So let's start with the first slide. And the next one. Okay, so this is about the motivation of the project. Why do we do it? Why did we get money for it from the National Science Foundation? So there are two major concerns nationwide, and the one is the future computer science and IT workforce. The sector of high technology is expanding rapidly, and the worries are that we don't get a large enough cadre of skilled workers to fill all these slots. The second concern is the computer-literate citizenry. Computers will affect more and more aspects of everyone's lives. Just throwing out ChatGPT as a recent development. So computers are here to stay in almost everyone's lives, and it's really important that people who are not computer scientists have some interest and some understanding of what goes on. So that's good for everyone. To address these two major concerns, there have been two major initiatives. One was to establish computer science in the school curriculum. That's a major sea change. Computer science has not been among the STEM disciplines taught in American schools traditionally, but there has been a push of establishing it in the schools as separate, as standalone courses, plus also as elements of other courses. So this is the in-school initiative, and parallel to that has been a effort to organize a whole variety of out-of-school time CS related activities. The question for our project now has been, do these initiatives work? Do they have any effect? Do they do what they are supposed to do? So these were the questions that motivated our project. And Rongju, if you go to the next slide, please. So these are the research questions, and from the title, you already can suspect that the setup was very complex because we have two dependent variables and two types of independent variables. So this slide is about the in-school independent variables. And we have 4 questions, and AB means 2 dependent variables, interest and identity. So the first question is, does a high school computer science course actually increase students' CS interest and identity? The second question, does the type of course, there are several flavors of computer science courses, AP and non-AP, make a difference? Third question, what about specific pedagogies in the classroom? Does it matter what the teachers actually spend their time with in computer science classes? And the fourth question is, does exposing students to computer science activities in other courses, for instance, mathematics, physics, or maybe even social science, have an impact? So these were the questions we asked about in-school computer science experiences. And now to the next slide. Thank you. And these are the questions about the influence of out-of-school time computer science experiences. So the fifth question is, can unstructured OST computer science activities predict students' CS interest and identity? These unstructured activities are things that students do on their own with little supervision, like using social media, playing computer games, and so on, hobbies. The sixth question is, what about structured activities? These are activities that have some more structure, some more formal, and usually supervised by adults, like extracurricular clubs, camps, competition, and so on. And last but not least, the seventh question is, what opportunities within programs, what are the things that people do that predict students' computer science interest and identity? Opportunities could include hands-on activities, working with older students, shadowing a computer science professional, and so on. And we had a whole range of these opportunities. So that's, in a nutshell, these are our questions. And Rongju, please go to the next slide. So this is the plan of the talk. I will shut up after this slide and turn it over to Sue, who actually made this study happen. She will explain the logistics and the data collection of the study. And then we will have Rongju for parts 2 and 3, where she will present the results that we found about first the in-school factors and then the out-of-school time factors. So Sue, the floor is yours.
Great, thanks. Next slide. So, as Gerhard mentioned, I was the project manager for the study and oversaw all the data collection. And so just to give you some background about the project a little bit more, these were our goals, which Gerhard kind of talked about a little bit. So the goal of the project were to look at the ecology of computer science. We wanted to find out who is involved in computer science and what's happening in these classes and these activities. And then what effect these courses and activities have on students' interest, identity, and career interest. Today, we're just going to focus primarily on participation in school, these courses, and OST activities, and CS interest and identity. So next slide. So how do you collect all the data to answer all these questions that Gerhard mentioned? Well, we used a retrospective cohort study. And if you're not familiar with that type of study, which most of the SED folks are, these are studies that ask students at a single point in time to recall experiences from their past. And they're very useful for data collection in that they're large scale, so you can obtain representative samples. They're more generalizable than small evaluations of specific programs, which are great if you want to learn about one program, but if you want to look across many, many programs, it's a good way to do it. You can test the strength of multiple hypotheses at the same time, which really helps. Again, big data set, lots of questions, lots of papers. And it can be completed in a shorter time than a longitudinal study. And that's sort of the gold standard, is to do these longitudinal studies, but they take a lot of time and a lot of effort and money. So this was a little bit shorter. So the next slide. Okay, so developing the instrument. So we developed the survey asking first-year college students to recall earlier CS experiences. And we created the questions based on a review of literature, a survey of stakeholders, both teachers in school and OST providers, and a survey of young CS professionals. And we had over 500 participate in that. And we pilot tested the survey with 100 students during the spring of 2021. And this is while classes were still remote, and also conducted a test retest asking the same students to take the test twice in 2 weeks. We made any necessary changes and then sent it out to thousands of students in compulsory first-year courses. And these were these English or writing courses, first-year classes that all the students have to take. We did this to get a wide range of both computer science and non-computer science students with broad career interests. The survey, the schools that we chose were, as maybe I mentioned, a stratified random sample of both 2-year and 4-year community colleges, and universities. And again, we did this to get the broadest range of students. So how did we do? Next slide. As I think Cindy mentioned in our intro, we were able to collect data from over 6,000 students across the country. Again, using a large scale study in a short time frame. We collected all of this data in 4 months in the fall of 2021, all during the late stages of the pandemic. So it was amazing that we got even this much. And big thanks to Annette Trenga for collecting all of this data. Next slide. So what did we ask? We developed a comprehensive survey of about 40 multi-part questions, and students could complete them in about 15 to 20 minutes, and we found that out during the pilot test. We asked questions about the subjects taken in school, grades, AP scores, if they took them. We asked about their participation in OST activities, and as Gerhard mentioned, these are both structured, like competitions and camps and lectures, talks, job shadowing, unstructured, so spending time on social media. A lot of that happened during the pandemic, playing computer games and talking about CS with family. And then these opportunities within the program or within activities. And as some other those might be working with on real world issues, interacting with mentors, working with older or younger students. We asked about CS interest, we asked about identity, and we'll show you those 2 questions in just a minute. We asked about their career interest and motivation, their family interests, and their involvement in CS, and demographics, as well as access to barriers. So we had a lot of questions, we have a lot of data, and Rangju's done a lot of analysis. So let's see what she found out.
Thank you, Gerhard. Thank you, Sue. Yeah, now I will be responsible for sharing some of the analytical results with you all. Yeah, so first, please allow me to introduce some demographic information of this project. So of all the more than 6,000 students who participated in the PICS survey, overall, we have 14% of students took a CS course, and those included like AP CSP, AP CSA principal, and non-AP CSA courses. And among those 14% of students who take the CS course, a high percentage, you can see from the figure, are boys, accounting for 55% in our sample. And this also reflects the gender differences in the field of computer science. So here is the comparison of the different as Gerhard give different flavors of the computer science courses to calculus and statistics. As you can see, in the computer science world, there is about 30% APCS courses, including 15% traditional APCSA courses and the same percentage of the APCSP courses. And this is a good comparison to the calculus, where the AP calculus AB or BC is about like a 34%. However, there is also there is a big comparison on the statistic. Big comparison to the statistic courses, where AP courses is dominant, taking about 30% here. So here is the a core CS course type by gender. So students can take more than one kind of CS courses, and those are the male and female students who took any kind of CS courses in high schools here. So we normally use the orange bar to represent the female students and the blue bar to represent the male students. And if there are asterisks on the top of the bars, it means the comparison between the groups are significant. So of those, as you can see from the figure on the left, boys are more likely to take the AP CSA course, and the girls are more likely to take non-AP CS regular courses. So now let's move on to the activities that occur during the most advanced high school computer science classes. And these are the particular activities that we ask the student to share with us, that how often those activities happen in the CS class in our survey. So we use different colors to represent the frequencies of these activities. As you can see, the blue bar is level, the orange is a few times, gray is monthly, yellow is weekly, and dark blue is every class. So see from the figure, robotics projects did not come quite often in those classes. It happened about just 30% in the CS class, and then it goes to the web page design, spreadsheets use, data analysis, collected CS to other subjects, everyday life, real life applications, and coding and non-coding. So here, the coding is quite popular in the CS class. About 30% of students, they said they coded every class they took. And non-coding here was computer science related non-coding activities, such as discussing computer securities, learning about computer hardware. So it is not quite as frequent as coding in the most advanced high school computer science class. Furthermore, to have a better understanding of the coding activity by different course type, we also broke the coding down by 3 different CS course type: the APCSA, APCS Principal, and the non-APCS CS. So we can see that in APCSA and APCS Principal courses, coding is much more like frequent and intense than that in non-APCS course. However, to our surprise, coding is found to be a little bit more frequent in the APCS principles than that in the APCSA course, which might be reversed from our like a common knowledge here. Then we are also interested in how in the computer science activities in the other STEM related courses. So first, we ask students how many courses such as biology, chemistry, physical science, and robotics the students take in high schools. So as you can see from the figure, in terms of biology, girls are more likely to take 2 courses, but less likely to take 1 course. And in terms of physics, engineering, and robotics, there is an advantage for boys in each comparison. And specifically, boys are more likely to take 1 or 2 courses in physics, engineering, and robotics. Then it comes to the question that how often does this computer-related activities occur during any of these non-CS high school classes? So the results are quite consistent across these CS adjacent disciplines. So in terms of coding, which are the 4 bars on the left of this figure, about 30% to 1/3 had coding activities. So either sometimes or often in any of the STEM courses. And in terms of long coding, which are the 4 bars to the right, they happen much more often than the coding, which are approximately 70%, such as the using spreadsheets and analyzing data occur in those courses. So above are some like general demographic information that we have for the CS activity in the high schools in the US. And now, I would like to share with you all the questions we use to measure the CS interest and the CS identity, and I will address the 7 questions one by one. So here, we ask CS interest at the end of high school. How interested were you in computing with a 6-point rating scale from 0, not interested at all, to 5, extremely interested? And CS identity at the beginning of college. How strongly do you agree or disagree with the statement? I see myself as a computer science person with another 6-point rating scale from 0, no, not at all, to 5, yes, very much. Now I'm going to answer the questions that have been proposed before one after the other. So the first question, does a high school computer science course increase students' CS interest? And here the answer is yes. And using like 2 separate figures, we show I show the comparison of CS interest and CS identity scores for students who select any of the CS courses. Here, any of the CS courses refers to the non-APCSA, APCS APCSA and the APCS principles. And in this figure, we can see that students who select any of the CS courses had much higher CS interest score than the student who did not take any of the CS course. And there is a statistically significant differences between these two groups. And so in this figure, we can also see the students who take any of the CS courses had the much higher CS identity than those who do not take any CS courses. So to get more insight, we also take the students' prior CS interest at the end of high school into our consideration. So we group the students into 4 groups. So here, the group 1 and the group 2 are the groups of students who had no CS interest at the end of middle school, but group 1 students, they did not take any CS-related courses in high school, and group 2, they did take any kind of the CS-related courses in high school, and these two groups, had statistically significant differences in their CS interest, and so in the CS education, we see these two groups of students relate to their students recruitment. Specifically, if you had no prior CS interests, taking the CS related courses can help the students to get into the relevant fields. And on the other hand, we also look at the students who had CS interest at the end of middle school. So for group 3 and 4, the students all had CS interest at the end of middle school, but group 3 here, they did not take any kind of CS related courses in high school, and group 4, they did take any CS courses in high school. So we can also see there is a big difference in these two groups. So usually we say these two groups of students relate to students like retention. So specifically, if the student already has their prior CS related interest, taking the CS related courses can help them retain their interest and get even more interested in the field. So so from this to the results, we can also say taking the CS courses, it did matter a lot in affecting students' CS interest. And this figure is the same logic with the different outcome CS identity. So so the results is quite consistent here. The student who had the CS interest at the end of middle school and took the CS related courses in high school had a much higher CS identity than those who had CS interest at the end of middle school but did not take the CS related courses. So it showed that similarly, the results, taking the CS related courses does matter a lot in affecting their CS identity. So following question 1, we would also like to address the question 2. Does the type of courses, those 3 types of courses, make a difference in CS interest and CS identity? And here the answer is still yes. So the left side of the figure, as you can see, showed that the student who had CS principals had much higher CS interest than the students who had non-AP CSA courses. And the right side of this figure shows that students who had AP CSA also had the higher CS interest than that for the student who had non-AP CSA. And here, the difference is not quite in the middle of this figure. You can see the difference is not quite obvious for students who take AP CSA or AP CS principal courses. And this is the result for the outcome CS identity. And for this result is also quite consistent as what we had in the previous figure. So specifically, student who had AP-CSP has much higher CS identity than the student who had non-AP-CSA courses, and student who had the AP-CSA had much higher CS identity than that for the student who had non-AP-CSA. And similar, no differences were found between students who take the AP-CSA and the AP-CS principles. And now, so it comes to our the third questions. Do these computer science related activities that occur during the most advanced high school CS class have an impact on CS interest and CS identity? And the answer is also yes. Yeah. So here the color green is a student who never take this kind of activities, and the color dark blue is students had some kind of activities. So we can see that participation in some of the activities, such as coding, designed, modified, tested, or debugged programs, programmed calculator, long coding, such as discussed computer security, learned about computer software, and collected CS to other subjects, everyday life and the real life applications, and as well as robotic projects, all increase students' CS interest at the end of high schools. And these are the participation of those computer-related activities in predicting the CS identity at the beginning of college. And this result is also quite consistent with that we have found out for the CS interest. So yeah, our next question 4, does exposing students to computer science activities, such as the coding and non-coding in other courses, have an impact on CS interest at the end of high school? And we have found out that coding in other sciences and non-coding in physics had an impact on CS interest at the end of high school. And specifically, coding in other sciences decreased students' CS interest, and non-coding increased students' CS interest. Non-coding in the physics class increased students' CS interest at the end of high school. So in terms of CS identity, non-coding in physics also increased the students' CS identity at the beginning of college. Yeah, and above are those the analytic results for students who participate the in-school CS related activities. And the next, we are going to talk about the impact of out of school time experiences on the outcomes we have, the CS interest and CS identity. And we broke those CS related activities into 3 different types. Altogether, we had 27 activities, in which we had 6 items that measure students' unstructured CS activities, 11 structured CS activities, and 10 opportunities within the CS programs. And all these items were developed based on the literature and the stakeholders. So here are the 6 unstructured activities. Not quite surprisingly, using the social media is quite popular with the 76% of students said they use the social media in high schools. And following that, playing computer games on computers or online ranked the second, with about 6% of students said they played games in high school. And the lowest percent of those activities are writing or modeling computer programs, games, apps, and with less than 20% of students said they had this kind of activities in high school. And here is a gender divide for those unstructured CS related activities. So we can see that the percentage of social media, creating online blogs, designing web pages, higher for the girls compared to the boys. And on the contrary, the percentage of computer games talking about CS and writing or modeling computer programs are higher for the boys compared to the girls. Yeah, so these are the structured CS related activities. Overall, we have the 11 kinds of CS, the structured CS related activities, and as you can see from the figure, students who participate in those structured activities were quite low, and all under 10%. So from the top, this is the activity that students participated most. You can see we had about 8% of students who participated in the CS related extracurricular clubs or teams at school, to the down below hackathons with just about 3% of students who participated in it. And I also did a comparison of those students' participation in those structured CS related activities across the gender groups here. So yeah, so interestingly here, no structured activities were significantly higher for girls. As you can see from the figure, all the boys all had a higher percentage of participation of those structured CS related activities. And here are the opportunities that the students experienced if they participated in CS programs. And similar with the structured activities, students' participation in those opportunities were also quite low and less than the 10%. And all those activities, except for mentoring or tutoring younger students, were statistically higher for boys. This result is like similar with the structure activities. So now we are going to address the question 5 to question 7. So yeah, specifically, we use all the like 27 items to measure those activities, and do those activities have an impact on CS interest and identity. So I use the green color to represent the students who never participated in those activities, and the dark blue to represent the students who participated, which includes like some or often in those activities. And we noticed that so all these 6 unstructured computer science related activities had an impact on the student CS interest. But specifically, as you can see from the figure, there are like five activities: writing or modeling computer programs, talking about CS, designing web pages, playing computer games, and creating online blogs. Those increase the CS interest, but using the social media, it's decreased the student CS interest at the end of high school. And this is the result for the unstructured activity in predicting the CS identity. And yeah, it had the similar results as we had for the outcome CS interest. The using social media also decreased a lot for the students' CS identity. Question 6. So we looking at the unstructured computer science related activities, and now comes to the structured CS related activities, whether this kind of events have an impact on students' interest and identity. And the result is are quite promising here. All these 11 structured CS related activities, they all increase students' interest at the end of high school. Yeah, and this is the result for the structured activities in predicting the CS identity, and the result is quite similar with what we had before. And all those activities had boosted students' CS identity. And this is our last question. Do those opportunities have an impact on students' CS interest at the end of high school? And yeah, and you can see all those 10 opportunities that students experienced in the CS programs. They all increase the students' CS interest. And this is the result for the different outcomes, CS identity, and the result is quite consistent and robust here. Both all increase the students' identity. Yeah. So you may, and then all the previous the effect of in-school and out-of-school activities were produced like in individual analysis. And you may also wonder if I put all those variables, unstructured, structured opportunities, as well as the in-school CS related activities and opportunities together in one regression model, which variables will still show the effect, and here are the results. So I put all those in-school and out-of-school variables together in one model, and I controlling for students' gender, race, and family factors. And we have found out unstructured activities, talking about CS with family, friends, and write computer programs, and opportunities, designing CS own projects, learning about CS career, and in-school factors such as the number of engineering courses, number of the robotics courses the students take, and coding in the most advanced CS class, all showed the positive effect in predicting our outcome CS interest. And the non-coding in other science, this variable showed the negative effect in affecting our outcome CS interest. And this is the result for the outcome CS identity, and use the similar logic. I put all the variables in one model while controlling for the student's gender, race, and family factors. And we have found out in unstructured variables, talking about CS with family friends, write computer programs, and opportunities, such as designing CS own projects, learning about CS career learning, and interacting with someone in CS career, as well as in-school factors, like taking one CS courses or two CS courses, and number of robotics courses, and coding in the most advanced CS course, and coding and non-coding in the most advanced CS courses, all had positive effects in predicting the outcome CS identity. Yeah, so those are pretty much all the results that we can share about with you all today. And thank you very much. And please feel free to let us know if you have any questions.
Thank you, Ranju and Gerhard and Sue. We do have a couple questions in the chat. One from Pat. Do you know if the CS classes were available at the schools for students who did not actually take computer science courses? Do we know that?
Gerhard or Sue, would you like to take these questions?
Yeah, no, we don't. So the result of this is that our estimates of the effect of the classes, for instance, are conservative. So that in reality, the effect of taking a computer science class is probably a little higher than what we have, because the group of non-takers is, in a sense, has higher levels of interest than it should have, because it includes a few who would have taken the class if they had the opportunity but couldn't. So the real effects are a little bit higher, but I don't think they're much higher.
Thank you.
And also, Mary, you had a question, and it's a little bit lengthy, so do you want to unmute and ask your question?
Yeah, for the in-school activities, Ranju had presented a slide in which she controlled for prior computer science interest, and you still, and she had that group 1 and group 2 and group 1 and group 2 where there was still an effect so the idea that these might be self-selected impacts because they were already interested in computer science was disproven. It showed that even if you were, anyway, but we didn't have a similar slide for the unstructured OST activities. And I realized after I asked the question, it might actually be because the numbers, it was tough to control for prior interest, but I don't know if you examined that.
Mary, yes, thank you so much for this question. We did have the, as you can see, we did have the one slide for the in-school factors, in-school variables here. But yeah, I think it's we should try to see the if what the results will be if we control for the interest for the out school activities. And we can check that later, but honestly, I haven't done that. Yeah, thank you. And it's not because the numbers were too small. I think I can still, I can still check to see the comparison. Thank you.
Any other questions? Feel free to unmute and ask your question.
Well, I have another question. I'll just toss in here. My question is about the construction of the survey itself, and I know it was done during the pandemic and it was handed out during the pandemic, and but there are some other activities that I don't know if I participated in them, and it's probably really small numbers, if I would see it in the choices you gave of unstructured activities. These days there's these the hour of code, which is like a big national event around coding. There's the unstructured activity of I think in earlier ones you had asked about Scratch and things like that. I mean, doing those, would that be in one of those questions? Things like that. There are more and more of these unstructured coding related activities that.
Yes. So Mary, I can jump in on that a little bit, and then maybe Gerhard wants to. If it's about programming specifically, we had a whole series of questions. Did you program, right? Did you? And then we said, and then there are a whole bunch of questions that went into which kinds of programming, block-based or, and Scratch was in there. And so those were not in with the activities that Rangjoo looked at. But there's a whole, because those do get into very small numbers of people who actually, and what age did you start? And when, we have all these questions about programming, and I'm happy to share the survey. And I think, is Darshan here? I think we have some people that are actually going to give you some data about that later this year.
Okay. Great. So answers to my questions forthcoming.
Perhaps. Stay tuned.
Go ahead, Pat.
Thank you. That was really interesting. So I'm wondering if you were to speak with like a superintendent of a school district, what recommendations would you make to them about how to structure things in their district?
I think based on the results we have found from the overall model, like the CSI, what's the variables predict the CSI identity stuff. For instance, it is recommended to take like a few more CS courses, like one CS course two CS courses, they are all good for the CS identity. Also some like hands-on CS related activities, learning about CS careers, and those those are the variables are quite robust in predicting our CS interest and the identity. Also, I noticed that like the talking about CS with friends or families around, this variable is also very robust in predicting the CS interest or identity, and even like the CS career interest, as we showed in our other presentations. This variable is quite robust. So yeah, it is encouraged for students to talk about that and get. I think it helps more for students to understand the foundations of those stuff.
Yeah, if I can add something, to me, the main message for the principal or whoever runs this thing is that the computer science courses work as advertised. Millions are spent on this, and that's a big change in the infrastructure of how STEM is taught in American schools. And people rushed into this without any empirical evidence, just hope. And that makes sense. Now let's put computer science into the schools. And this study provides some empirical evidence that it actually worked. And often, and we all know this, that often educational initiatives made with really a good heart and great hopes don't pan out empirically. And a lot of waste ensues. And so that's, I think, the main message to these policymakers, that there's a case where it actually worked to some extent. So it's good. It works better than these things in physics and math courses where we didn't find that effect. So yeah, if you want to increase computer science, career interest, identity, have those courses.
And I just want to,
Sorry, go ahead, Sue.
I just wanted to add one other piece that came not from our data, but data that we collected from young professionals and students who are in CS right now. And when we were building the survey, there's still a big stigma around CS, and there's both positive, oh, it's a lot of money and you can do things, but there's a lot of negatives to CS, especially for women. And that came up, well, I was interested, but it's all boys. I was interested, but it wasn't, right for me. So yeah, I'm agreeing with what Mary's saying, finding ways to make it more approachable, interesting. And that's, again, getting more into career than interest in identity. But, you don't always get career interest until you have some interest in identity. So it's a start.
Thank you.
Thank you. Go ahead, Phil.
Yeah, this was really good to see all this analysis. I want to build on what Gerhard said, which is the comparisons I think are really important. That comparing this to other fields, like does taking a physics course increase your physics identity or want to be go into physics or engineering? I mean, we actually have measures of that. So if what you're saying is true, CS seems to be more effective than these other courses. It would be really interesting to see that comparison. And I agree, there's lots of innovations that people really believe will have a big effect. And then when researchers actually do the study, like putting physics first, physics, then chemistry, then biology, it turns out that it doesn't have the effect that that people have that justify its promotion. So this appears to have that effect, that CS courses and other out of school activities are very beneficial in terms of getting kids interested in the field. I mean, they could have just turned everybody off. People will often look at this and say, oh, well, this is obvious. Not obvious to me that a course in high school is going to increase your identity and your interest in the field. I think a lot of the opposite happens for a lot of kids.
Pat, did you have another question? Okay. Any other questions? I'll just follow up on one thing that Raju mentioned. Oh, sorry, Alex. She talked about how talking about computer science has an impact on interest and identity. We do have a seminar coming up in March dealing with that very topic about the impact, and it's a big impact about talking with STEM or talking about STEM, whether it's with family, friends, and classes, et cetera. So that's coming up in March. Alex, you had a question.
Yeah, thanks. Yeah, this is a great talk, and it's nice to see all this data after you've worked on it so long. What about causality and correspondence? What do you know that the people who take the computer science courses in high school are already interested, and therefore when they get to answer the questionnaire, they're just going to show their interest? Can you have any distinction between people who took required courses versus, electives in computer science? And is there a way to test whether adding a computer science is just going to increase interest in people who weren't otherwise already interested? That's my question.
Can I answer this? This is like a chicken and egg question that we labor with in virtually every project we do. The gold standard to really get at causality would be to take a school and randomly select half of the students and give them a computer science course and prevent the other half of the students from taking that computer science course. Certainly, in Cambridge, that would lead to a revolution, because the parents would say, you cannot do that to my kids. I or my kid, we decide where to go. So real experiments in science education, or I would say in education in general, are rare, are hard to do. And so we labor with these correlational studies, and you're absolutely right. These are correlations where the causality is not really proven beyond any reasonable doubt. I mean, the thing that we do, and that Rongju has shown with those 4 different groups, we try to control for prior interest. So we have this kind of a temporal sequence. So we know kids are interested or not interested at the beginning of high school. Then they take or do not take the course, and then we look at the outcome. So this is some control, and I have to say, this is better than most of the courses, most of the studies that are done in this field, because they don't go back and they don't know at all. So my short answer is yes, you're right, and we're trying to control for prior interest as some kind of a mechanism to assuage that problem, but we cannot solve it unless we do experiments.
And go ahead.
Oh, hi, Bob. Thank you for the wonderful presentation, and congratulations for your work. So I've been thinking a lot about this question lately. I don't know if you have answer based on data, but I'm just curious about your opinion. Is that the students are busy and their plate are very full, and we know that to do more in anything, they will benefit more, right? But given that if we can, if the plate is fixed, the amount of space in the plate is fixed, what would be a good combination of structured and unstructured activity? Like if you were to design a package of CS experience, what would be a recipe that you would offer, right? Like what is there a sweet spot of a mixture between structured and unstructured activities? Do things work better together? Are there a couple of stuff that work better together?
Well, I think that was the last slide, at least for the out of school time. When you put them all together, when you run the regression model with everything, those are the ones that come up strongest, correct, Ranju? As opposed to the other ones were individual regression models, right? So that they all came out great, but when you control for lots of things, these come out the best. Is this?
Yeah, from a statistic point of view, when we combine those kind of activities together, those showed best results in predicting our outcome. Yeah, but I'm not sure if what Chen asked is related to the statistical results, or is that like should be answered by like practical people?
Yeah, I mean, I think Chen's question. Oh, sorry.
No, go ahead, Mary.
Right. It seems like we need more information, more fine-grained information about the quality of the different experiences for different people. Because, you know, clearly there were some differences in participation just among girls and boys, and you haven't presented other demographic data, although I know you have it and we'll look at it later. But that question of, is there a sweet spot of participating in unstructured or out of school time activities along with maybe taking a course, because you can see, first of all, many more kids have an opportunity through school to have a computer science experience. It's very clear. Many more have an opportunity. But you know, if you were gonna, I think that's a really interesting question to contemplate.
From a statistic point of view, is I think I'm envisioning something like a profile, right? Like a latent profile. That there are a couple of things that tend to happen together as a package, and if it happened together a lot, at least it means it's manageable by some individual, and maybe some profile works better than other profile. No.
Right. So taking one course, because you've got a limited plate of things to do, one course plus out of school participation in a coding club.
Yes. That could be one way to partially answer that question.
Phil, go ahead.
Several people brought up this idea of, you know, causality versus correlation, and certainly controlling for interest is one way to make it to make a better causal argument. I mean, there are many of us in the group who have used much more sophisticated statistical methods, like a propensity weighting or propensity matching, which get you even closer, but they're more complicated, harder to do. You need to just test a few things rather than the kitchen sink. So one way to think about it is that 1/7 of the kids took a computer science course in high school. You can take each one of those kids and search through all the rest of the kids to find a kid who's similar in initial interest, in whether their parents were in CS or STEM, whether they were boys or girls, etc. And you can match people who had this particular experience with people who did not have this experience, but are basically the same. And then you can do regression analysis on this post facto matched group. And we have done that a fair amount. And you often get similar results to a simpler method, but this propensity methods are we do like to use, but they're harder to use, and you can only test a few hypotheses that way. But to answer people's question about causality versus correlation, this gets you much closer because it's a pseudo experiment where you're splitting people into two groups with all these different measures, trying to get two people who are almost exactly the same as close as you can measure. Does that make sense, Alex and Mary?
It does, yeah. I think it's hard to say. You could also do a similar thing where you took people who had bad experiences in computer science courses and see if that decreased their interest. Mm-hmm. Which we don't want to advertise those, but I'm sure that happens too.
Sure.
Any other questions?
Did you find an experience that works for one gender but doesn't work for the other gender? I know that you've always been interested in gender differences. Did you see a interaction effect?
Rangju, you have that data, you know that.
Yeah. Yeah, we did test it. We did test the interaction effect. Yeah, if I remember correctly, the talking about CS with family and friends, this boosted a lot for boys rather than for the girls.
Oh, interesting. I found that very surprising.
Have you ever found the similar results or
I don't know. I mean,
results?
just intuitively, I think that's surprising.
Yeah, I would have expected the opposite, but yeah, that's interesting.
It's some kind of Matthew effect, yeah.
Any other questions from anybody? So we'll thank our presenters, Drs. Sonnert, Sunbury, and Wu for an outstanding talk. I put in the chat the link where you can find this talk as soon as I get the cloud recording, and we'll post it to our YouTube channel. And you can also access all of our other seminar talks at that channel as well. I also posted, as soon as I hit go in the chat, our February talk from Dr. Skonlieber of Sonoma State, looking at culturally responsive science curriculum, particularly focusing on Hawaiian cultural-based education and diverse learners, which may be of interest to some of our CFA colleagues who are affiliated with the telescopes and learning in Hawaii. So we want to thank everybody for attending. What a wonderful attendance for early on in July after the Christmas break. And please join us again for our future seminars. Thank you, everybody.
Thanks.